Hi! In this video we're going to talk about billboarding. First off, we'll start by telling a little about what the concept of billboarding is, followed by how and for what billboarding can be used. Afterwards, we will present our own simple billboard effects and go through the code and explain what is going on.
In its most simple form, billboarding is to make flat objects automatically rotate, so they always will be parallel to the camera or be oriented towards the camera point. This can help create a simple illusion where flat objects seem like they have a bit more volume to them. This is often used to replace some 3D objects to make games run smoother by reducing polygons. It is mostly used where high detail is not needed, and where the same type of object is needed to be repeated many times. Let us take some few examples.
Grass could be one place where billboarding could be wanted. If you were to use 3D models, you would have hundreds and hundreds of grass straws consisting of relatively many polygons to make the grass straw look smooth, which would demand quite a lot from the computer to run. With billboarding, these models could instead be replaced with 2D textures and reduce the process power needed. Billboarding can be a fine solution due to the grass normally does not need a very high level of detail and will therefore not ruin the look of the game. The type of billboards chosen for grass will probably most often be billboarding type called axial billboarding. This is also used for trees or any other tube-like objects. When using axial billboarding, the billboard planes will only rotate around a fixed world space axis. This means that it, for example, only will rotate with the camera in Y rotations. An example of a nice grass billboarding can be seen in this short clip.
Smoke and other particles is another example where billboarding is often used, due to the huge amount of object instances created when representing, for example, smoke. When making billboarding for particles, viewplane-aligned billboarding is often used. Viewplane-aligned billboarding means that the billboards at all times will be parallel to the viewplane as seen on the left. On the right, another billboarding technique is used. This is called viewpoint-oriented billboarding, and in this case, all billboards instead rotate to always face the viewpoint position. This third type of billboarding is great for creating imposters, especially in first-person 3D games, where wide field of view often are used. The viewpoint-oriented billboarding technique resembles a natural distortion of objects when they move towards the edge of the view. Viewplane-aligned billboarding techniques does not resemble this. Here you can see the difference. The upper left sphere has a viewplane-aligned shader applied and is not distorted. The upper right has a viewpoint-oriented shader applied and is slightly distorted. The two bottom spheres are normal sphere objects and represent the natural distortion.
In our own example of billboarding, we have created a small environment where you can walk around. In the environment, we have implemented 4 different billboards. We have implemented 2 billboards with GPU shader programming running on the powerful graphical processing unit, while the 2 other billboards are created by normal CPU scripting running on the central processing unit. Another difference is that the CPU billboards are what can be categorized as static or offline imposters or billboards, because this is simply 2D textures plastered on a plane. The GPU billboards can instead be categorized as a dynamic imposters or billboards, because this code actually automatically converts a 3D object into a 2D texture plane by rendering an image of the 3D object to a texture at runtime.
We have created both CPU and GPU billboarding to show that billboarding is not limited to only one of them, but can be done with both methods and still save processing power by exchanging 3D models with 2D textures. However, for optimal optimization, it is preferable to stick to GPU programming, due to that the GPU is way more efficient compared to the CPU. The GPU contains thousands of cores in parallel architecture, which can handle multiple tasks simultaneously, whereas the CPU only contains multiple cores optimized for sequential serial processing. A nice example of the difference is the Mythbusters/NVIDIA live show, where the first smaller robot represents CPU and the large air gun represents GPU.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9,
8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
As the last thing in this video, we'll take a look at our code and explain what is happening. First, the C# scripts or CPU billboarding will be explained. We'll start with our viewpoint-oriented billboard. It is fairly simple. In the start function, the scale on the set is set to -1, so that we can actually see the image on the quad. If this was not done, we could see the backside of the quad, which is completely transparent. Then in the update function of the viewpoint-oriented script, the transform is simply set to look at the camera.
Second, we have our actual billboard. In the update of this, the transform is again set to look at the camera, but as it's only supposed to rotate around the y-axis, what we do is to check on what side the camera is of the quad's center and use that to find the angle from the normal rotation, 0, 0, 0, to the rotation the quad have when looking at the camera. The angle is then used to rotate the quad around the y-axis. That was all for the C# scripts. We will now look at the GPU billboarding scripts.
Our first GPU billboard is a plane aligned billboard. It is inside the vertex shader that everything is happening. What it does is to first flatten the 3D object, then the x position of the vertex is subtracted from x and z is subtracted from y. This is done because it is a plane. Had it been a quad, y would have been subtracted from y instead. This makes the plane be parallel to the view plane of the camera.
Our second GPU billboard is a viewpoint-oriented billboard, just as our first CPU billboard. The important aspect of this shader happens in the geometry shader, which is happening after the vertex shader in the shader pipeline. If we look at the mathematics for 3D programming and computer graphics book, at page 254 to 257, we see some math for making billboards, which is also used here. First we find up. In the book it is defined as up for the camera. It is however used here as a world up. Then the direction from the object to the camera is found. This is then used to find right by crossing them together. We then make a plane for each vertex sent in. These planes will then always face the camera. We find each corner by adding and subtracting up and b from the center. The text coordinates are also set to each corner of the plane compared to the book page 255. We first set Q4, then Q1, Q3, and last Q2. Setting them in the order specified in the book will give an incorrect image. Last, we will then take the vertices and project them to the camera, and then append them to the triangle stream, which will not take in more than 4 vertices as specified just above the function.
Our last and third GPU billboard is an actual billboard. The shader does much the same as the one just examined, but it is constrained in its rotation as it can only rotate around the y-axis, just like the actual billboard in C# mentioned earlier. The only thing different from this and the viewpoint-oriented shader mentioned before is that we no longer take the cross product of up and right.
That was all. Thank you for listening.